Hi, good morning, everyone. It looks like already 10 a.m., so let's get started with our webinar today. So today we are going to talk about specific absorption rate simulation with ANSYS HFSS. So first of all, I want to show you guys a quick article before we get started into the HFSS project. So this is a white paper that was created by ANSYS engineers. So this paper is talking about how smartphone impact on human body. So here we can see as we may know in while there are many different standards for the specific absorption rate limit. So in the US, the FCC requires the SAR values to be below 1.6 watts per kilogram. So as you can see in this paper here, we have a cell phone right next to the human head. So in this part here we can see we have the different operating frequency and the different SAR values for different different weight of uh different weight density. So here, so on the left hand side here we can see that there's a with different frequency the field, the SAR field that impacts on the human head is differently. So from left to right is 900 megahertz, 1.8 gigahertz, and GPS, which is 2.4 gigahertz. So if we're scrolling down, we can see this is a human head. We have the brand. So one thing about ANSYS is we have human detailed human body model. So which we have the skins, we have the that includes all the details layers like skin, fat, and also all the organs inside the human body. So next part, so with this one, so we can see that this one is showing the also the human head with the cell phone right next to it. If we keep scrolling down, so this is the full human body, and then if we put the cell phone inside the pockets, so that's how it impacts how the SAR looks like on the human body. So and we can also get the values for that. So if we keep scrolling down, there are more. Yeah. So this is just a quick overview of what HFS can do. So but next, then I'm going to jump into our today's design. So today, what we have is a simple MRI system. So this is made of just a simple coils with some tuning capacitors on it. So other and then we are going to simulate this first, and after this we are going to have a gel models right between in, inside these coils. So we are not going to use the human body. We are not going to use the real human body today because that will consume um a lot of simulation time. Okay, so first of all, HFSS allows you to import many different type of geometries. So here you can see we can import CAD file, we can import parasolid file, we can import SolidWorks file, etc., step files. So you can, if you create your model in other tools, you are always welcome to import your design here. And next thing is we need to set up the material properties and the excitation ports. So I'm making everything simple here, so we can see that we are using sheets. So this is a 2D object instead of like a we are not using there's no thickness in this case. So but if you import your object, you are always welcome to assign a material to that. So in this case we don't have it. Yes. So I have everything like this coils. I have a finite connectivity for the material properties. So I'm using copper for it. And next, we have all the lamp ports. These are all the excitations. So you can see here, this called the cap bottom, cap top. This means they are the tuning capacitor here. So at the beginning, we are not adding the capacitor value here because we are going to link this with another tool called Circuit Designer, and then we can add our capacitor values to it. But if your design is already optimized and you know your capacitor values, then you are always welcome to just set the values here. So you can basically right click, assign boundaries, and then you can set the lump RLC values for it. So here you can enter your capacitance value, in resistance value, and inductance value. But yes, so after there are many ports, and then we only have 4 ports is our real excitation. So you can see it's here, and all the other ones will be our tuning capacitors. Okay, so another setup we have here is we have a airbox. So because here I'm having multiple different mesh size because I'm trying to reduce the time for the simulation. So with larger structure, I just give you a larger mesh size. With smaller structure, I just have a smaller mesh size. And you are always welcome to change this to anything that you like or to have a higher accuracy. And next step is we're going to add a solution setup. So we'll add advanced, and in this case, I'm not doing any frequency sweep. So I'm just set the frequency at the operating frequency is 6.8 giga 6.33.8 megahertz. Then we have the setup here. We set up a number of iteration that you want to run the simulation. But as soon as the simulation is converged, it won't run any more iterations. Yep. So this pretty much looks good, and you can go ahead and validate your design. Once everything is green, we can go ahead and analyze it. So because of timing issue, I am cutting this short. So I already simulated this design, and we can go ahead and look at some results. So the first thing we want to to verify your how your MRI coil perform, there are a few things we typically looking at. So first, of course, we look at the field. So we can look at the magnetic field, and we can look at the um, electric field. So I'm going to go ahead and plot the field here. I just select a plane. I'm going to go ahead and right click on field overlays, plot fields, and I can plot the magnetic edge field. Okay, so I'm going to select the right frequency, select the right phase. I'm going to done. Okay, so I can have scaled it to be log scale. So we can look at some magnetic field. And same thing. We can go ahead and look at some electric field. Right, so log scale. Yeah, so in this case we don't have a uniform field because we are not adding the tuning capacitors to it yet. So but once we add the tuning capacitors, then we can see the field. So yeah, we can add another one to the YZ plan. Right. So if we look top down, no, this is maybe like this. Yeah. All right. So we can look at the YZ plan for the E field. For the E field, we can look at the YZ plan for the H field. This is very simple, right? Okay. So next is we are going to um link the design to um we want to link up the tuning capacitors. Okay, so I'm going to go into project. I can insert circuit design. I click done. Okay, so now the next thing I want to do is you can either right click copy and paste, or you can just drag and drop. So now we have our design here. So I'm going to arrange the pins a little bit, or actually I don't have to. Next I'm just going to add some capacitors to it. So I have the capacitors here. I just add the capacitors. Okay, I'm just going to copy a string of it. Make my life easier. Right. Okay, maybe it's a bit too many. Just delete two of them here. Looks good. Just copy the string to the other side. Actually, let me change it here first. Let me give it a variable. So I will just have them all named cap. You see that 1.9. Yep. Unit type, capacitors, picofarad. Okay. I guess I have to name it all. Don't really. I forgot to do copy paste. Okay. Anyways, cap. I'm just too lazy. I'm going to do copy and paste. Okay. Let's. All right. So copy the other one too. So the good thing about setting up this variable is if you have the design parameters here, then you are able to run the parametric analysis. So you can actually tune your capacitor values up and down to see how it changes, etc. So I should also copy the wire. But yeah, this can be simple. Let's copy it. copy, paste, paste, paste. Okay. This, delete this too. Copy, paste, paste. I'm going to give them a ground. Right, they are all having the ground, and then just link it up all to the ground. Okay, now I have the model set up. So, oh, sorry, I forgot. Here are the ports. So I shouldn't have the capacitor here. Copy too fast. Yep. So now I can just copy all of this. I'm going to give them a port, right? This, and this. Okay. All right. So next, if we check all the ports, they looks good, then we can go ahead and go to the excitation. We can configure source. For each one, we can add, add a excitation to each port. So let's say what is the magnitude for, I will just put 1 volt. And for everything, I think just leave it as it is, or you can just give it a frequency 33.8 megahertz. That looks good. Yeah, so apply. Okay, then I'll just use the same, I guess. Can I? Okay. All right. Yeah. So I want to create multiple ones. With and let them have the phase different. So I should have this one. I should add another one. Okay, can I copy? No copy for this. So I just add another port. Also 40, and this time I want to give it a 90-degree phase difference. Okay. Next one. 180. Alright. What's next? 270. Okay. So next thing we will need to do is add the analysis setup. So I'm just going to add a single point frequency, linear network analysis. Add just single value 33.8. Okay, looks good. So let's analyze it. Okay, looks like the simulation is finished. It's just that quick, like a snap. Yeah, so next we can add a parametric. So not next. If you want to do a parametric analysis for your capacitors, you can always add parametric and then add the capacitor. You can tune it for different values. Then let's say I have this. I have this, and then what's my step? My step is let's say 1. I add it. Okay, now I have this, right? But I don't want to do it right now. So if you want to try out something like this, feel free to let me know. Yeah, after the simulation done, we want to push the result back to our 3D design, so we can right click on the model and then push excitation. It's okay. And now we can go back there. Oh, I forgot to save the field from earlier, but now you can see that the field is a little bit uniform than what we had before. Right, for the magnetic field. Yeah, so but you are always welcome to fine tune it. Right now it's not that, it's somewhat uniform, but not quite. Um, yep. So this is what we have, and next, I'm going to bring in the gel so we can actually see the SR value, the SAR value, for this one. So to do that, we need to first. So the first step is of course set up your MRI coils, have everything done like the field, and make sure your MRI coil meets the performance that that you desire. So after that is done, we are going to create a 3D component for the MRI coil. And how to do that? I'm going to copy this one, and then I'm going to create another one, and so we don't mess up anything there. Um, yeah, so to create a 3D component, that is very easy. You just need to delete the setup, then you are ready to create the 3D components. So now we go to the draw 3D component library, create 3D components. Oh yeah, I need to select them. Select everything. Draw and create 3D component, right? So yeah, Yifan Yang, this is me. And then you can put down your information here. Because once your design is created as a 3D component, it will become a encrypted. It will become a You can lock it and it will become an encrypted model, so other people cannot look what is inside it. So here is you can encrypt your model, uh, but I'm not going to do that. So here from info we can look at everything what is included in the selected components, the boundary, the excitations, circuit elements. We have the mesh setup, the coordinate system, and etc etc. So you just need to click OK and then save it as a 3D component file. I can just save it. MRI coil, right? Mm, Save. Okay. Okay. So once we save this, the next step that we want to do is we want to create a blank design. Not project. Sorry. Let's close this. Design. So here, go to project. You can insert another HFSS design. And the first thing we want to do here is we want to call back our MRI coil. Um, so we can go to draw. the reason that why I want to use the 3D component is because once the model is already tuned and the design is already set, I don't want to change anything of the design. A 3D component can make sure you, while you are doing other simulation, you don't mess up anything with your with the MRI coil. So we can open this. All right, now we have the MRI coil. So here you can see this is our 3D component, and it listed under the 3D components here. And when you bring it over, you will also include all the excitation that you have defined. And next thing, we are going to. Oh yeah, so I was telling you, we are not going to put a real human head, human body in this case. So there are two type of human body that ANSYS has. One is just a very simple human body. So here in the component library, we have the human body extension. Or yeah, so we have female or male. Even though there's no really big difference for the arm and head. So yeah, so we can just select a head with drag and drop. Now we have the head here, and right. So this, but look at the if we look at the head, this is also a very simple. This is also a 3D component, and it only has one material property. So it's called a human average, but the dielectric constant, everything is um, it's just approximate the average dielectric of the human body. So most likely to be water. Um, so and now we just need to move this thing in between the the MRI coil. So I'm going to draw, select the head. I'm going to use, can I? Cannot. Okay, now I can isolate it. I use a move, and then select some points on the human head. Da, da, da. X, Y, Z. Okay. Select it. I'm just going to slide it, put it somewhere here. All right. So I have the human head right in between the MRI coil. Right. So now I can go ahead and next thing I need to do is I need to have uh air box. Sorry, couldn't come up with the name. Yeah, so I need an air box. So I just go to the model, right click, create regions, and just simply enter your operating frequency. Then boom, it will create an air box automatically. Where's the air box? Right, it's right here. Okay. So now we have air box. We have boundary. We have excitation, and do I want to add a mesh? Yes, I do. I can. Yeah, I can. I can give the human head right click. I can assign the mesh to the human head. So I just select the human head, right click, assign mesh operation on selections to component. Oh, okay. Yeah, so what I need to do is I need to go to the human head and then assign it there. So in this case, I can just edit definition to open the human head. Because the human head is not encrypted model, so I can do it. I can change it here. Yes, so now I just go ahead and same thing, select human head, mesh. Right, so I will just set 50 millimeter, even though the default is like 50. If you save this, it will be saved automatically. Next thing I want to add analysis setup. Just do it for a single frequency and more iteration 20. Click OK. So I don't need any sweep. And go ahead validate it. Every single screen, and now I can have it ready to run. So yeah, so I have a soft model. So this is what I have here. I'm just using a gel to simplify the simulation time here because the human head has some curvature and is a quite complex geometry. It has nose and eyes, so it might take a little bit longer. Here we have the gel and then it's already simulated. Um, one more thing to mention is when you create the 3D components for the MRI coil, the circuit is not included. So when you have the like human hair or the gel inside the coil, um, what you need to do you can just delete the center part and then copy and paste over and then just hook it up again. Where it goes, right? Right. So you just hook it up again. Um, then you should be then just run it, right? Everything should be the same. And then just run it, analyze. Right, we have the progress is here, analyzed, and then it should be done quickly, and then just push excitation. Everything is the same. And now we have the result. Let's look at our SAR value, SAR value. Okay, looks great, looks great. So next I'm going to show you how to plot the specific absorption rate. So in HFSS, there are two types of specific absorption rate that you can plot. One is called the local SAR. So I can show you it's right here when plot field. Other, there's local and average. So local SAR, when you calculate the local SAR, HFSS uses the equation at each mesh to calculate the SAR at each mesh point on an overlay plot. So and HFSS interpolates the value between the mesh point across the plot. So in this case, you can think of it like you just plot the SAR value on the surface, but without there's another thing is called the average. Another plot is the average SAR. The average the HFSS calculate the average SAR by subdivide the model space into a group of voxel properly and then align along the global coordinate system. And then the density and the local SAR value are then mapped over the grid of the voxels. So the when you have either when you define your own material property, can I oh here when you either define your own material property, or you choose a material from the ANSYS library, you can see there's a mass density here. So either you enter your mass density here, or if you right click on if you leave it blank there or 0, if you right click on the field overlay, you can do the SAR setting. You can also change it here, right? So yeah, the so after the mapping is over, HFSS will apply the two-pass average SAR algorithm to the voxels. Finally, HFSS distribute the average voxels, the average SAR from the voxels back to the FEM mesh. So in this case, we can get the SAR over over volume over density. So and because this two-pass algorithm is very time consuming, and when it's trying to calculate the SAR over volumes, it will take up a lot of time. So HFS use the parallel processing as much as possible to reduce the time in this case. So yeah, so next is we are going to plot the results. So here we have the average SAR. So I'm just plotting on a plane like I showed you. I'm just plotting it on a YZ plane, or I can plot it like as a volume. So if I choose the gel here, right? So if I choose them and then I plot fields, average SAR, um, you can choose to plot on the surface only or not, but I will choose to plot it as a volume. So do I have anything come up yet? It's loading. It's coming up. There we go. And now we have the SAR over volume. So here we can clearly see where it has higher SAR values. Right. Or if you just want to check out the maximum the as the SAR value, then you can go to the results, right click, create field report and data table. So now we have this, and you can just plot at a single frequency. You need to choose a point. So um, um, here I think the point we have here is at the center. So I'm going to just you can do this. You can draw a line. So yes, I want to create a null model. I can draw a line. So let's say I draw a line along axis, right? So when I create the data data table, I can choose the polling line that I just created, and then average SAR, right? So here I have the frequency, I have the phase. You can use all phase or just use one. If you choose all phase, you create a new report. Maybe all phases is too many. But yeah, so here you can have from at different distance what is the SAR value, and at different frequency with different phase, right? So if you are just interested in uh, if you are just interested in finding the maximum average SAR value for this for the human body or for the gel, you can do this. Go to field overlay calculator. We can do that is we can choose average SAR, copy to stack, and then I want to geometry. I want to choose the one of the implant box, right? That's the human body. I take integral and choose maximum. Where's maximum? Max. Let's see. Oh, right here we have the maximum values. Okay, so maybe not integrate. I need to undo that. I need to use domain and then use the maximum values. Let me see what I need to do here. Okay, so I don't need anything here. So when I choose the average and value, I just choose maximum values, and then when eval, I can find the maximum SAR value in this case. And now we have the maximum SAR. Yeah, so this is very simple to do. And I think, yep. So what was coming next is last but not least. So this is another magic about HFSS is you can change the excitation, right? So you can right click excitation edit source, and here you can change the change the power of input. So I think like here we have 4 watts, 4 watts, 4 watts, 4 watts. So these are the values. Um, these are the values that was pushed from our circuit, but you can always change it here. You can always change the value here. Let's say you have 0 for all the others, and you have you can change the power input here. Like let's say we change it to 8 watts, 8 watts, 8 watts, 8 watts, right? Apply. Then we will have a different SAR values. So you can adjusting the power input for your system in this case. So the total power in this case is 32 watts. Right. Um, so it takes a little bit of time to, right. So now we have a, right, now the SAR, the view is looking a little bit different. Yeah, so So I think this will be all for today's webinar. So um, if you are interested in this topic, and if you want to do some S SAR simulation with HFSS, feel free to reach out, contact me, or excuse me. So feel free to reach out and contact me, or contact the link, the email attached below. So we are happy to give you a trial to provide you some experience in HFSS. So yeah, and looks like we still have 15 more minutes left, so I will stay on a bit. Please let me know if you have any questions. Yep. So if not, then I will talk to. I am looking forward to hear from you. Oh yeah. So if you're interested in the white papers or anything, feel free to email me, and I'm happy to share. All right. Have a good day, guys. Bye.